Hello everyone, good evening. Welcome back to the solutions for BSDS sample paper 2024. We're at question 23 now, slowly inching towards the end of the series. I hope you have been enjoying all of the solutions given to you. If you have any doubts or if you spot any mistake in the videos, do let me know in the comment section. We will correct and or issue any explanations if needed. Alright, if you need any help with the course, do contact the numbers given in the chat box. They will redirect you to the appropriate help. Alright, so what is question 23? Question 23 states define a relation tilde on R3 as x tilde y if there exists a matrix such that y equal to ax. Then what is tilde? Now the solution to this problem is quite easy. This is basically a problem on linear transformations. Now as a separate chapter, linear transformations will only be there in your graduation course of linear algebra. Alright, so this portion is not yet there in your class 11-12 syllabus, but the concept is quite easy and I found the solution in a graduation textbook. Alright, so I have the solution for you all and I'll just explain it bit by bit. So the relation, as I told you, it is just based on linear transformation. So what is linear transformation? Linear transformation is exactly what it is defined here, right? There will be a matrix A which you can apply to any matrix Y to transfer it to X. Now why is it linear? Because there is no powers here, right? It goes from one point to the other. So you basically apply a transformation. Why do we need transformations? Because not all of the data that we get are usable in the format that they have been gotten. Alright, so we might need to change some of them. So if we need to do that, if we need to change anything, then it's always better to use a transformation. Alright, now how do we apply the transformation? The concept of that will be taught to you in the linear algebra chapter when we go through linear transformations in most likely first or second sem of the graduation course. You will learn these. Alright, so linear transformation is an equivalence relation. Alright, it's written there outright, so we know we will have to mark option A. Now how do we prove that this is an equivalence relation? So let us go through the proof. To prove that something is equivalence, we have to show it's reflexive, symmetric as well as transitive, right? So let us go through these portions one by one. Now reflexive means you have to map x to x itself. Now that is possible due to Ax, where A is identity matrix. So if you put the identity matrix, you will have x equal to Ix, right? That is possible. Now for this, x will relate to x, therefore the relation is reflexive. Now symmetric, because if x relates to y, then there exists a matrix A such that y equal to x. This implies that A inverse exists, assuming A is invertible. So if your transformation is invertible, then x should be equal to A inverse y, therefore y should be related to x, and therefore the relation is symmetric. Now there is one problem here, that the function is defined on the entirety of R3. So we will have the null matrix here as well. The null matrix here is not invertible. Alright? So there creeps up a matrix where we cannot guarantee that A will always be invertible. So if we cannot guarantee that A will always be invertible, then we cannot guarantee that second property. Right? Is there any condition in the question that forces us to conclude that A will always be invertible? No. Since there is nothing given in the question relating to that, we cannot assume anything outside of it. Alright, so although the relation on linear transformations is an equivalence relation, but there is no guarantee there. So for now, we will put a star here. This occurs assuming A is invertible, but it may or may not be. So transitive, if x relates to y and y relates to z, then there exists matrices A and B such that y equal to x and z equal to by. Substituting the expression into the second gives z equal to ba into x. Now we can multiply the two matrices, right? Since they are from R3. If they are from R3, then they can be multiplied easily. Matrix multiplication we have done. So relation is transitive. Now this satisfies all three properties of equivalence relation, assuming A is invertible. But if it is not invertible, then the symmetric property will not be there. Right? So just to be safe, we will not be marking option A, we will be marking option D. Reflexive and transitive, that is there for sure. Okay? But not symmetric. Again, for most A's, where the determinant of A is non-zero, it will be invertible and symmetry will hold. But it is not given anywhere the determinant A is non-zero. Right? I can create any number of matrices in R3 where A will not be invertible. And if A is not invertible, then symmetric won't hold, right? We can only go from y to x and not back to y. Since there is no guarantee, although linear transformation as a concept has equivalence to it, this you will study in the first year of graduation, as I told you. But in this particular sum, there is no guarantee. If there is no guarantee, then we mark option D. Alright? Hopefully you understood why I started with the proof of equivalence relation, and I showed you why it would be wrong to assume certain things that are not given in the question. Alright? All of us know that linear transformations are equivalence. Alright? Because we have studied the chapter that is there in linear algebra. But here there is no guarantee. Okay, so whatever you have studied relating to any theory, relating to any question, please make sure to focus it within the lens of the question that's being asked. Here there is no information on A or the invertibility of A. So we cannot conclude symmetricity for guarantee. And if we cannot conclude that, it's always better to mark option D. Alright, because equivalence is a very strong relation. Right? All three have to be there together. Now we can for sure say it is reflexive and transitive because I can multiply any 3 cross 3 matrices, right? They are in R3. So multiplication is there, but there is no guarantee on invertibility. Okay? Even the null matrix is not excluded here, right? So the null matrix is there, so null matrix will always be non-invertible, right? So that transformation will cease to be symmetric. That is a hallmark option D. Okay? So I hope you understood this question. If not, rewind the entire logic, watch it, you will understand. And if there are any questions relating to this, do put them down in the comment section. And if you need any help, please contact the number that is given in the comment box. Alright? I'll see you all in question 24.